All right, so a couple things about roots and what I've done with this video is basically what I did is I took either looking at that quiz, I either took problems exactly from that quiz or problems very similar to it, and just so in that way you'd have an opportunity to practice some that were similar to the quiz, so in that way you could practice again or put it into practice when looking at the actual quiz. But like I said, some of these problems that I'll go through are actual problems from that quiz. And I noticed that, so obviously this is covering roots, and so we're going to break this down into basically 3 different sections, so I'm guessing are the same sections that you went through it when you're going through it in class. The first would be just how to simplify roots, and then how to add and subtract roots, and then multiplying and dividing roots. And out of all of that, dividing, when you're dividing by roots, I think is the most difficult. And if you struggle with any of this stuff before then, it's going to make dividing by roots even that much harder. So it's really important that we understand the basics, and so that's why we'll start there. So first off, one of the first things you need to recognize is that when you're dealing with, so you have, well, first off, you have different types of roots. You have even roots and odd roots. So even roots would be like the second root, the fourth root, the sixth root. So those are obviously even roots. And so when I talk about an odd root, that would be like a cubed root, a fifth root, a seventh root, and so on. So when you take an even root of a negative number, it's not possible. Okay, if you think about just this, even let's start with something basic. The square root of negative 9. Remember, a square root is looking to see what 2 numbers multiply together that would give you that value. Well, there's no 2 numbers that I can multiply together that are the same that would give me negative 9, because negative 3 times negative 3 would be a positive 9. So there's no 2 numbers that I can multiply together to get a negative answer. So anytime, and so that would be true for any even root. So anytime you have an even root of a negative number, it's going to be what's called a non-real solution. Now, odd roots, if you have an odd root of a negative number, now that's possible, because if we have the cubed root of negative 27, for example, that's possible, because negative 3 times negative 3 would be a positive 9, but positive 9 times negative 3 would be negative 27. So if you have an odd root of a negative number, your answer will always be negative. Okay, and then, so I'm just going through those bullet points. And so the third bullet point is going to come into play when we look at that second example. And that's if you ever have a exponent, whether it's a number with an exponent or more specifically a variable with an exponent, all that you got to do is take that exponent, that power, and divide it by the root. And I'll explain more how that works, because when we deal with an actual example, it'll make more sense. But the cool thing is when you learned in elementary school this idea of a remainder, that term actually makes sense in this situation, because whatever the remainder is remains under the radical. And lastly, if you ever need to simplify a root, some teachers teach you how to solve it using perfect squares, but I always struggled as a student memorizing all those perfect squares, and so what I enjoy doing, even though sometimes it took a little bit longer, is making a factor tree, because then that can be used in any situation without having to rely on just memorizing a bunch of numbers. And I'll show you how to do that with the third example here in this first segment. So let's start with that first one. So here we have the square root of negative 64. So anytime you have a root that doesn't have a number there, remember that's a square root, so this would be a second root. So here we have a second root, so an even root of a negative number. So it's not possible. So in that case, your solution would be that there are no solutions, or you could say that the solutions would be non-real. Now for the next one, we have an odd root of a negative 27. Now it looked to me from the work that I saw, your teacher taught you to break this up into separate pieces, which is totally fine. That's sometimes the way that I tell students, what I tell students to do. So if I were to work through this one using that method, we would look at this as a cubed root of negative 27, and then we would have the cubed root of x to the fourth and the cubed root of y to the sixth. So let's look at those individually. So like I said, the first one there, we have an odd root of a negative number. So I know my answer is going to be negative. And so now I want to look to see, well, what times itself 3 times would give us 27? Well, it's actually one of the problems I just talked about. The cube root of 27 would be 3, because 3 times 3 times 3 would be 27. So the cube root of negative 27 simplifies to be just negative 3. Now let's look at x to the fourth. So what that means is I have 4 x's. Okay, x to the fourth means I have 4 x's. So when we're dealing with the cubed root, we're looking to see sets of 3, we can factor one out. Okay, so if we have 3 of the same item, we get to factor 1 out. So if I have 4 x's, I get to factor 1 x out, and I'm left with 1 remaining. Technically, that's what's happening. So your answer for that piece would just be x times the cube root of x. Otherwise, we could go back to that third bullet point and use division. And you could say, well, 3 goes into 4 one time, so you get to factor out 1x. 3 goes into 4 one time with the remainder of 1. And that 1 would remain under the radical. So that 1x would remain under the radical. So whatever's easiest for you to look at. So looking at that last piece, y to the 6th power means I have 6 y's. So for every 3, I get to take 1 out, okay, which can be kind of tricky to use with fingers once you get to use too many. So here's what I'd like to do, is I like to say, well, 3 goes into 6 2 times. And it goes in there evenly with nothing remaining. So there's not going to be any y's remaining under the radical. But, like I said, 3 goes into 6 2 times, so we'd factor out a y squared. So now if we put this all together as 1, we would have negative 3 and then x y squared. So that's all the items that would be outside of the radical. Then underneath the radical, we'd have the cubed root of x. So that would be your answer there for that second one. Now for the third one, this is one where, again, maybe your teacher would taught you with memorizing perfect cubes. Again, that just gets to be too confusing, too much. And so what I would do is I would use a factor tree. So that's what I'm going to do with this one. So what I mean by factor tree is we're going to look for 2 numbers that multiply together to give you 192. Now, I don't know them off the top of my head, but I noticed that 192 is an even number. So I'm going to take 192 divided by 2. And when you do that, you get 96. Now, when I'm doing this, I like to circle my prime numbers. Because what can often happen with the factor trees, you can get to using a lot of numbers, and it's really easy to miss some of those prime numbers. And so that's what we're looking for. We're breaking this down into the prime factors. And so anytime I get a prime number like 2, 3, 5, 7, 11, anytime I get a prime number, I circle it so I can remember, I can have a visual to see where all my numbers, where all those prime numbers are at. Okay, let's look at 90. So 2 is prime. 96 is clearly not prime. It's even. So if you're looking to see what 2 numbers multiply together to give you 96, well, 2 times 48 is 96. Now you can break up 48 into 2 times 24 and keep going that way if you wanted to, but you're just looking for any numbers. So you can do 4 and 12. You can do 6 and 8. It really doesn't matter. I'll do 6 and 8. And then 6 breaks down to be 2 times 3. There we go. And 2 and 3 are both prime. Okay, so I'm going to stop with those. But with the 8, that breaks down to be 2 times 4. 2 is prime. 4 breaks down to be 2 times 2. So that would be the prime factorization, is what we would call that. Now let's look back at what we're dealing with. We're dealing with a cubed, whoops, I have to highlight that. We're dealing with a cubed root. So for every 3 of the same number, we get to factor 1 out. So here I see that I have 3 2's. Here I see I have another 3 2's. So for each of those groups of 3, we get to factor 1 out. So I get to factor out a 2 for that first set, a 2 for the second set, and then we're left with a 3 underneath the radical. And 2 times 2 would be 4. So your answer here would be 4 times the cubed root of 3. Okay, so now let's look at this next piece. If you're ever multiplying roots, the nth root needs to be the same root. So meaning that if you're multiplying like the square root times a cubed root, you can't do that. They have to be the same root, which your teacher's not going to do that to you. I hope that they wouldn't do that to you because that's just a waste of a problem. So you always just want to make sure that you're dealing with the same roots. So everything has to be a cubed root, everything has to be a square root, whatever the root is, the nth root needs to be the same. And then what you're going to do is you're just going to multiply whatever's under the root together. So for this one, I see that we have a square root. They're both square roots, so I'm going to put both of these under the same root. So we would have 18 times 2. I'm going to multiply those together. Then we would have an x cubed times an x squared, so we're going to multiply those together. And then we would have a y cubed. All right, well, let's actually do some multiplying there. So 18 times 2 would be 36. We'd have the square root of 36. Now, when you're multiplying variables, remember when you're multiplying two variables and the bases are the same, remember the bases are what sit on the ground. So when the bases are the same, you add the exponents. So x cubed times x squared, they have the same base, so we would add the exponents. 3 plus 2 is 5. So we would have x to the 5th power. And the reason why we add the exponents, if you don't remember that, x cubed means we have 3 of them, x squared means we have 2 of them, so when you're multiplying them, you put them together, you have a total of 5. All right, so then the y cubed, there's nothing to multiply there, so we would just have this. And now we're just going to simplify this like we did earlier. Okay, we're going to, and again, if you want to break it apart like your teacher might have showed you, so we would have square root of 36, the square root of x to the 5th, and the square root of y cubed. So square root of 36, well, that's just going to be 6. The square root of x to the 5th, again, that's a square root, that's an even root. So 2 goes into 5 2 times, and then we'd have a, whoops, so that should be an x squared. 2 goes into 5 2 times, and so you would have x squared, and then you'd have 1 remaining, because 2 goes into 5 twice with the remainder of 1. So we'd have 1 remaining under the radical. And with the square root of y cubed, again, that's a square root. And so 2 goes into 3 just 1 time with the remainder of 1. So we would have y times the square root of y left over there. So your final answer, when you put that all together, you'd end up, I didn't really leave myself a whole lot of space, I'll put this up above here. You'd end up with 6 x squared y times the square root of xy. Okay, so whatever's outside of the roots, you put those all together, so we'd have a 6 x squared and y. Whatever's under the root, you just put those now back under a single root, so we'd have the square root of xy. All right, let's look at adding and subtracting fractions. So just in simplest terms, when we're dealing with adding and subtracting radicals, I think I said fractions a second ago. When you're adding and subtracting radicals, you want to make sure that what's underneath the radicals is the same value. Because when we're adding and subtracting radicals or roots, it's like adding or subtracting like terms. Okay, so if I had 3x plus 5x minus 4x, you know that we could combine those all as 1. So the same thing here works with roots. We want to have the same thing under the root. And if they're not the same thing under the root, we want to figure out how to simplify it first, and then more than likely now you're going to have the same number underneath the same root, and then you can combine those together. So with this first one, I just kept it simple there. This is an example that I made up just so you could see the concept. So here we have all of these are square roots of 2. So now we can combine those. So 3 plus 5 would be 8, and 8 minus 4 would be 4, so we'd have 4 square roots of 2. So your answer would just be 4 square root of 2. Don't do anything with the square root of 2 underneath there. They are just simple. They're just like terms. Think of them like an x. If you had 3x plus 5x minus 4x, you know your answer would just be 4x. You didn't, you've done it so often you haven't, you don't wonder, well, wait a minute, what about the x's? How do I add? You added those together already by saying that you had 3 of them, you had 5 of them, and you took away 4 of them. So you had 8 and you took away 4 to get 4x. So same thing here. We have 3 square roots of 2's, we have 5 square roots of 2's, and we're taking away 4 square roots of 2. So it's just like working with x's. All right, now the next one, cube root of 128 and the cube root of 54 are clearly not the same number under the root. So I have to simplify both of these. And so I don't know what the cube root of 128 is, so I'm going to use that factor tree method that I like to use. So the cube root of 128, so I know that 2 times 64 would be 128. And now 64, that breaks down to be 8 times 8. 8 breaks down to be 2 times 4. 4 breaks down to be 2 times 2. And then this 8 breaks down to be 2 times 4. And 4 breaks down to be 2 times 2. So again, every 3 of the same, since this is a cubed root, for every 3 of the same number, we get to factor 1 out. So I'm going to factor out a 2. I'm going to factor out another 2. So 2 times 2 would, so I'm going to kind of go through both of these, go through this all in one step. So we'd have a 2 and another 2 that factor out. And 2 times 2 would be 4. And be left with a cubed root of 2. So that would be 4 times the cubed root of 2. Okay, now with the 54, I'm going to have to kind of squeeze this in here, so I apologize for that. 54, that breaks down to be, well, 9 times 6 would be 54. 9 breaks down to be 3 times 3, and 6 breaks down to be 3 times 2, and those are all the prime numbers. And so here I can see that I would have one set of 3's that are all the same with the 2 left over. So that one set of 3 we can factor out, so this will be minus 3, and be left with the cubed root of 2. So if you notice now, we have the same number under the same root. So we have 4 cubed root of 2 minus 3 cubed root of 2. So we just treat those now as like terms. So 4 minus 3 would be 1. So your answer would just be 1 times the cubed root of 2, which is the same as cubed root of 2. So if you wrote down 1 cubed root of 2, that's fine. And I believe that's one that was off of your quiz. All right, I don't know why my screen does that sometimes. All right. There we go. Now it goes away. All right. Let's get to dividing by roots now. Again, dividing by roots are the hardest part of we're working with radicals, working with roots. Dividing by a root is the hardest thing because you have two different situations. We could have a situation where there's just a single term in our denominator with the root, which is the first one we're going to look at. Moving down to the other option would be if we have two terms in the denominator, and one of those terms is a root. And when we have those two situations, we have to approach those in two different ways. So let's start with this first one. So anytime we need to, if we have a single root in the denominator, we're going to do what's called rationalizing the denominator. So rationalizing the denominator just means to get rid of that root. So we just have a nice little number or a nice little variable in our denominator. So all we're going to do to rationalize the denominator is we're going to look to see what's missing. So here we have 5 divided by the cubed root of x. So what's missing? Well, in order to take the cubed root of x, I'd have to have the cubed root of x cubed, because 3 would go into 3 evenly. So that means that I'm missing an x squared, because x squared times x would be x cubed. So I'm going to multiply the top and bottom by not just x squared, the cubed root of x squared. Because remember, they have to be underneath the same root in order for us to be able to multiply those together. So whatever we do to the denominator, we have to do the same thing to the numerator. So I'm going to multiply, like I said, the top and bottom by the cubed root of x squared. So when I do that, I would have 5 times the cubed root of x squared in the numerator. In the denominator, we would have the cubed root of x cubed. Now the cubed root of x cubed, well, 3 goes into 3 one time, so that would just be x. Now this would be your answer. Okay, that would be your answer. A lot of students make this mistake and they see that, oh, well, we have an x here and that x squared, so can we simplify that? Can I cancel out the x from the denominator and take away an x from the numerator and just have the cubed root of x? No, you can't do that. Okay, I tell my students that a radical sign is kind of like this box that you can't penetrate that box. Okay, you have x-ray vision, you can see what's inside that box, but you can't do anything unless it's taken out of that box. And so the cubed root of x squared, I can't take anything out of there, so I can't do anything with that. So don't try to do anything with something that's inside the box or inside the root with something outside the root. Okay, so the x squared that's underneath that radical, I can't do anything with that. So this would be your final answer, 5 times the cubed root of x squared over x. Now, if there was something outside of the radical in the numerator that you could reduce with the denominator, then yes, then that you can do. But if it's underneath the radical, it's trapped. You can't do anything with it. All right, let's look at these now. So now here we still have a single term in our denominator, but the one thing I recognize is we have a root in our numerator and a root in the denominator, and they are the same root. So what you can do in that situation is before you start multiplying, because when you start multiplying and doing all that, it really gets ugly. So if there's anything we can do to reduce it before we multiply, we want to do that first. So what you're going to do, and I noticed that you did this in your quiz, is you are going to combine this underneath a single root. So I would have the single root of 72 x cubed y to the 5th. So all of that would be in the numerator. And then we'd have 2xy squared in the denominator. So now we have this all written, just like when we multiplied, if you went back to what we did here with this example, where we had the square roots and we were multiplying, we combined those under the same root and then simplified. So we're going to do the same thing here with dividing. So since we're dividing here, we're going to put these underneath the same root and then simplify. So underneath that root, I can see that I can reduce, because 72 divided by 2 would be 36. So we'd have the square root of 36. And then x cubed divided by x. So remember, when we're dividing and the bases are the same, what we do is we subtract the exponents. Okay, so 3 minus 1 would be 2, so we'd have x squared in our numerator. And with y to the 5th and y squared, sorry, that squared is not very good here. There we go. That y to the 5th and the y squared, again, they're the same base, we would subtract the exponents. So 5 minus 2 would be 3, so we would have y cubed there. So now we want to see what we can do to simplify this. And so again, if your teacher taught you how to break this up into separate pieces, you can. Just for space sake, I really don't have a lot of space left over, so I'm just going to break this up. Square root of 36 would just be 6, so that worked out nicely. The square root of x squared, well, 2 goes into 2 one time, so we just factor out an x. The cube root of y cubed, 2 goes into that exponent, 2 goes into 3 one time. So we'd factor out a y, but we're left with 1 remaining. So 1 is going to remain under the radical. So square root of 36 would be 6, square root of x squared would just be x, and the square root of y cubed would be y times the square root of y. And that would be your answer. Now this is one I believe that was actually on your quiz. So let's look at how we would do this one. So again, we have the cubed root. Both the numerator and the denominator have the same exact root, so we can combine those. So we would have 270x in the numerator and 10x y squared in the denominator. So now let's see what we can reduce from that fraction before we do anything else. So the one thing I recognize is that 10 goes into 270 27 times. So we would have, underneath the cubed root, we'd have 27, and then the x's would cancel out. So we would have, and the 10 would be gone as well. So all we're left with is we would have 27 over y squared, all under the cubed root. Now remember, they're still under the cubed root. So what I could do at this point is I could break these up into separate roots. So we could have the cubed root of 27 over the cubed root of y squared. Now the cubed root of 27 is just 3. So now we have the 3 over the cubed root of y squared. Now fractions are really finicky. There's certain things that we can't do with the fractions. One of those that we can't do with the fractions, we can't have a root in the denominator. So just like we talked about in that previous example up here where we had 5 over the cubed root of x, we have to get rid of that root. And so what I need to look for is what's missing. I already have y squared. In order to take the cubed root of that y, I would have to have y cubed. And so I'm missing another y. So I'm going to multiply the numerator and the denominator by the cubed root of y. Okay, so now when I do that, I'd have in the denominator, I'd have the cubed root of y cubed, which is just going to be y. And the numerator, we would have 3 times the cubed root of y. Don't multiply the 3 times the y inside the radical either. So the thing about that box, the radical, is we don't want to put things into it, okay, unless it's already underneath the root. So the 3 is not under a root. The cubed root is, or the cubed root of y is under the root. So that when we combine those, don't multiply the 3 and the y together. Okay, because I've seen some of my students that would do that. They would have the cubed root of 3y as their answer. That's wrong. It's not parentheses where we distribute. We would leave the 3 outside of the root. So we'd have 3 times the cubed root of y over y. And then, like I said earlier, don't try to cancel out those y's because that y in the denominator is not under a root. The y in the numerator is. It's trapped. You can't do anything with it. So this would be your final answer for that one. All right, let's end by looking at, well, what happens if we have 2 terms in our denominator? If you have 2 terms in the denominator, you multiply by the conjugate. And the conjugate, and I'm pretty sure when I looked at your quiz, I'm pretty sure that this is what you did. I saw that you did take 3 times, or you did multiply by the conjugate. And so this first example is one that I made up. The second example is one then where you can maybe even practice it. So one thing that you can do is you can pause the video maybe when we get to that one and try it on your own to see if you can get it. But let's look at what we would do with this first one. So we have in our denominator 3 minus the square root of 5. We don't worry so much about what's in the numerator right now. All we worry about is rationalizing the denominator. So we're going to multiply the top and bottom by the conjugate of the denominator. So the denominator, we would have 3, or the conjugate of 3 minus the square root of 5 would be 3 plus the square root of 5. So I'm going to multiply the top and bottom by the square root of 5. Now here's the deal with the multiplying by the conjugate. I'm going to show you a trick, but I'm going to show you first why the trick works. Also, I saw that when you were multiplying, your teacher taught you like the FOIL method, which is great. For me and for some students, that can get kind of sloppy because everything's all linear in one line. I'm going to show you something that might help you, especially when we multiply the numerator. So let's look at that denominator. So we're going to be multiplying 3 minus the square root of 5 times 3 plus the square root of 5. So this is how I like to do it. I call this the box method. It just keeps things a little bit more organized. So I have 2 terms, and I'm going to multiply by another 2 terms. So I create a 2 by 2 grid. And then I put those factors on the outside. And just like kind of like a times table or multiplication table, we're going to multiply those outside pieces to get the inside pieces. So 3 times 3 would be 9. 3 times negative square root of 5 would be negative 3 square root of 5. And square root of 5 times 3 would be 3 square root of 5. And square root of 5 times a negative square root of 5, well, square root of 5 times square root of 5 is just square root of 25, or 5. And so we would have negative 5 there. Now notice what happens. 3 times square root of 5 minus 3 square root of 5 is 0. They disappear. And then we're just left with 9 minus 5 is 4. So here's what I want to show you. When you multiply by a conjugate, you don't have to go through and do this whole box method. We will for the numerator, but for the denominator, you don't have to. Because no matter what, if you ever multiply by the conjugate, these two will always be opposite terms of each other. They'll always be the same thing, only opposites. And they're just going to end up being 0. And we're just going to be left with whatever the first numbers would be, whatever the last numbers multiplied together would be, and we just combine those. So here's what I tell students. I'm going to erase this. When we multiply by the conjugate, I tell students, just multiply the first 2 terms and the last 2 terms together. It's much easier. Because again, those other terms would cancel each other out. So 3 times 3 would be 9. And a negative times a positive will always be negative, because that's what we'll always have when we multiply by the conjugate. We'll always have a plus and a minus. And square root of 5 times square root of 5 is just 5. So 9 minus 5, I know, is 4. Okay, so you can save yourself that work of having to do that box method. But for the numerator, we do, if we have 2 terms times another 2 terms, we do have to use that box method, or the FOIL method like your teacher showed you. But I'm going to show you again with this box method. So we'd have 4 plus the square root of 5, and then we would have 3 plus the square root of 5. So when you multiply those together, 3 times 4 is 12, and this will be 3 square root of 5. The next row, square root of 5 times 4, will just be 4 square root of 5, and square root of 5 times square root of 5 would just be square root of 25, or 5. So we'll combine like terms. 12 plus 5 is 17, and then we combine our roots. Those 4 square root of 5 plus 3 square root of 5 would be 7 square root of 5. Now, if you could reduce this, if maybe, let's say if the numerator, let's say if you had 18 plus 8 square root of 5 all over 4. And I noticed that each of those terms would be divisible by 2, with the 18, the 8, and the 4. All of those would be divisible by 2. Then I would reduce this fraction by dividing everything by 2. But here, nothing can be reduced. There's nothing that goes into 17. 17 is a prime number. 7 is a prime number. And 4 is not. So those can't be reduced. So this would be your final answer. So if you feel like, so this last one kind of puts a lot of those problems, a lot of the things that we've just talked about all together. So if you would like to try this on your own, you could pause the video and try it, and then I will still show you how to do this one, so you can hit play to see if you've done it correctly. Otherwise, if you just want to carry on and watch me do this, you could do that. So I'll give you a second. You could pause it now and then try it. All right, so let's see if you did pause it. Let's see how you did. Okay, so for this one, I'm going to multiply the top and bottom by the conjugate of the denominator. Whoops. So it'd be 10 plus the square root of 7. What we multiply the top and bottom by. Now remember, just like the previous one, when we multiply with the conjugate, all we have to worry about multiplying together is the first terms and the last terms. So 10 times 10 would be 100, and it'll always be minus, and square root of 7 times square root of 7 would be 7. And so 100 minus 7 would be 93. So our denominator would be 93. But let's look at the numerator. So for the numerator, you're still going to want to use that box method or the FOIL method. When you're doing this box method, by the way, it doesn't matter which, if I put the 3 minus 2 square root of 7 on top or the 3 minus 2 square root of 7 on the side, it doesn't matter. You'll still get the same answer no matter what. All right, so let's multiply these together. So 10 times 3 would be 30. 10 times negative 2 square root of 7 would be negative 20 square root of 7. And square root of 7 times 3 would be 3 square root of 7. And then lastly, square root of 7 times negative 2 square root of 7. Well, let's think about that. Square root of 7 times square root of 7 would be 7. And then we'd have to multiply that times a 2. So we'd have negative 14 here, because we'd have negative 2 times 7. And now we combine like terms. So 30 minus 14 would be 16. And 3 square root of 7 minus 20 square root of 7 will be minus 17 square root of 7. And that can't be reduced at all. So that would be your final answer. So hopefully that helps you out there. If you have any questions, feel free to email me if something wasn't clear, or if you had a question just about why I did something. I don't want to just assume that you knew everything here, so hopefully that was enough information for you to be able to make those corrections on your quiz. And like I said, feel free to reach out to me also during my office hours, and I'd be glad to help any way I can. So good luck.